Yes. Hello, everyone. Hey, Ezra, can you see my screen and hear me?
Yeah, it's clear.
Okay. All right. Good. Okay. Hello, everyone. Thank you for joining the Quantum Forum. This is Professor Kalok. I am one of the co-chair of the Quantum Computing Research Center. This activity is organized by me and Professor K.T. Huang and Mr. Alex Dunn. He's also one of our speaker for today. Right now, before I start, let me briefly introduce about the aim of this forum. This forum is to provide a platform for learning the basics and the latest developments of quantum science and computing, a cutting-edge field that explores the power and potential of quantum physics for computation and information processing. We hope this forum is able to inspire and motivate you to pursue your curiosity and passion for quantum science and computing, and to equip you with the necessary skills and knowledge to understand and apply quantum science and computing concepts and techniques. Now we have a website, https quantum.asia.edu. So by following this link, you will see a page like this. Then please click on this link. This will carry you to a new homepage. And down below, we have a link for you to sign up for our activities. So if you follow that link, please fill in the Google form to sign up. Just sign up once, no need to do it again. We will keep your information in our database. And we also call for a welcome for presentation, call for presentation. So if you are interested in hosting a presentation, so please go to this website, this link, call for presentation, and then download the form over here and send it back to us, okay, for approval. Now, subject to the speaker approval, we will send you the lecture notes and the link of the video recording, usually within 5 days after the presentation. Okay, we have organized a lecture series titled Quantum Machine Learning, its Biomedical and Physical Application. Today, this is the third event, okay, April 29th. We have 2 more coming up. So you are welcome to keep it in your calendar. Okay. So please refer to the poster for detail. So today we are really pleased to have 5 speakers, and the first one is Ezra Wijaya. Okay. So before the presentation, let me introduce. Dr. Ezra Wijaya. He is a passionate researcher based at Binawan University in Indonesia, where he is interested in the realms of diagnostic, biomarker discovery, and precision medicine. Ezra's academic journey commenced with a bachelor degree in medical science of physiotherapy from Binawan College, Indonesia in 2010. Laying the foundation for his career in the medical field. He's eager to explore the intersection of biology, biological, and technology. He pursued a master's degree in biomedical informatics at Asia University, Taiwan in 2015. Finally embarked on a transformative journey, accumulating a doctorate degree in biomedical and medical engineering from Asia University, Taiwan, in earlier this year, January. Throughout his academic pathway, Ezra has been dedicated to unraveling the mysteries of the human body, leveraging innovative methodology in medical science through informatic technology. So for that, let's welcome Dr. Wijaya. So let me stop sharing, and let me pass my microphone to Ezra.
Okay, thank you very much, Professor. So let me share my screen. Okay, thank you for your time and also introduction. So as Professor Kalok mentions, I am graduate from Asia University, but my first major is not in computer science, but in the medical health science. So in this case, I try to give you understanding about the field that I am working on right now, and also what the idea that I will do in the future. So today we are not just here for a presentations. Of course, we are here to share an idea and also ignite curiosity and maybe even challenge the different topic in bioinformatics. So excuse me, Professor, can you see my screen right now?
Yes, I can see. I can also, yeah.
Okay, good. Thank you. So let me give a sneak peek into what is in store for the learning today. We're gonna break it into small piece of informations from what can we learn from bioinformatics and what is the innovations in healthcare and also the final statement. So also I'm gonna give you more informations why we need actually quantum machine learning compared to the classical one. Right, so the beginning of the topic is what can we learn from bioinformatics. So if you are not from bioinformatics fields, not also from the biology field, so this is will be the new information for you to learn about the bioinformatics. So our first topic is what can we learn from the bioinformatics. So you can imagine the healthcare research paradigms in modern age has been bestowed with numerous advanced and innovative that we have more revolutionized our comprehensions of health and illness. So before at the times like long time ago, we are using some traditional methods just based on paper, report, and so on. And then right now, because we have computations, we have IT system, we have storage systems, then we can change our point of view, how we're gonna approach the healthcare. In this case, of course, the innovation will help us to elevate from traditional diagnostics methods to more tailored and also specialized treatment modalities. So we are more advancing before we have disease that we cannot cure, but because we have more technology in the computer science, that we can more dissect the information about the rare disease, for example, or maybe for example, like before, like 2 years ago, we have COVID, then we can use the informatics systems and also algorithms to solve what is COVID itself. Now, we're gonna moving from the basic concept, very basic concept about bioinformatics. So when you said about bioinformatics, it's actually interdisciplinary. So this is bioinformatics. Uh, it consists actually from different field of study. One of them is biology, the other is computer science, and we also have math, and the last one will be statistics. So we are combine all those fields. Not everything we learn in biology, not everything we learn in computer science, like not all major topic in computer science we learn, but part of it, like part of biology, part of computer science, part of math, and also statistics, it become um, one major curriculum called bioinformatics. But the real reasons why this exists is because we are sought to study about the DNA. So if you see the picture in your screens, So we try to see what is the, we try to define what is chromosomes, what is the DNA, what is the histone, for example, what is the genes, what is the nucleotide, and so on. So we are focused in this field is focused more into like molecular biology. So it's like a small thing in biology. It's related to your genetics and also the variations of the genetics. Now, so bioinformatics is also play a crucial role to derive meaningful insight from biological data. So remember, each data in biology, we can connect those informations and try to create some conclusions and also hypotheses about what is right about disease, what is not right about the disease. So in the next slide, I try to explain more about the example, how we try to get the information, the data, from fresh into the data. So in bioinformatics study, usually we're gonna have the real patients, which is the real humans. And also from this human, for example, we have patients. In this case, let's say we try to use, I'll give you some illustrations about the bioinformatics research. In this case, it's okay if you never heard about this research before. It's about the single cell RNA sequencing. Basically, we try to sequence the DNA from this patient, for example. Now, remember, if we took some sample in our patients, for example, like this, in here we have the tissue. Tissue is the part of like a group of cell that we try to dissect into from our patients into our tube, for example. Now, in this case, human consists not only one single cell, but actually it consists of the different combination of cell which they have their own regulations in our body. Now the sample taken from patients and also they put it into some machines which using the Chromium 10X. This is just method you can skip if you don't understand, it's okay. This method is try to identify the different cell types. Remember, we have like a brain cell, lung cell, skin cell, and so on. So they try to, for example, in this case, it try to separate which cell belongs to what cell. Okay, for example, this one belongs to cancer cell. This one belongs to immune cell, for example, for B cell or the lymphocyte or white blood cell. And for example, the other will be the stromal cell. So Chromium 10X is actually a technology to differentiate and also give some kind of coloring to certain type of cell based on the biomarker. So in here, we can categorize the cell that we took from this patients into, for example, into cancer, normal, and also immune cells. Now, the unique in this case, in the biology, we have a machine. For example, in here, we have next sequencing 500. Now, these machines will copy your DNA, synthesize using sequence machines, and it becomes tagged with the unique barcode sequence. So we can know what is the sequence belongs to the cancer, what is the sequence belongs to the normal cell, what is the sequence belongs to white blood cell, what is the sequence belongs to the stromal cell, and so on. Now, remember, every machine we're gonna produce, we will produce some data. So what kind of data provided by the sequencing machine? So if you are learning about the IT, most of our data will be text data. So mostly text or maybe string, which consists of 4 different types of DNA code. A, T, C, and here is AT, CG. And this is the combinations of the sequence for single cell, for example. They're going to produce some long DNA sequences, and based on these sequences, we try to understand what are the difference between cancer sequence, gene sequence, and also what is the difference between the normal cell gene sequence. Now, this information is very complex. So that's why it produces a lot of data. And based on this data, we need to train our algorithms to reclustering. Now maybe you can relate with your field, or we can cluster between the normal cell and also we can cluster with the cancer cell, which is true. This is what we've done in bioinformatics. We try to separate which one is normal, which one is not the normal one. And of course, using the algorithms like IT algorithms, you can say machine learning, deep learning, or maybe like high advanced algorithms like quantum machine learning, then we can create some kind of modeling to predict, for example, in this case, the cell signaling prediction. We can give predictions how many percent it will lead to cancer from the normal cell, how many percent it will be mutate into different cell. Then using the computations, we are able to achieve that kind of information. Now, the most important part is also prognosis in patients cohort. So we have several data, start from the patient data and also start from the cancer data until the genetic data. Now, based on this data, we can predict how many percent of this patient will be survived in 5 years or maybe 10 years. That's why you maybe watch in the movie, like doctor give some kind of prognostic, while the patient asking, how is my family? And the doctor said, oh, probably he will live only until 3 months, or maybe live until 1 year or maybe 2 years. So those informations are based on this kind of method and also a systematic procedure. Now, aside from the computations, then we can try to validations. Validation, it means that we test again in the lab. We try to simulate again in the lab. In this case, we can try to test like in vitro for the functional assay, or maybe tissue IHC validations to test whether certain cell will be have their own actions against some kind of immune system. If we add some kind of chemical, for example. So this informations will give us a lot of point of view when we learn about the bioinformatics and how we apply algorithms in computer science into biology. So learning about bioinformatics, we try to extract not only genes, a lot of information we can extract from like single cell or maybe like several cells, for example. We can predict, we can see the descriptions about people's genome or epigenome. So genome is about DNA, epigenome is outside DNA, but also controlling your genetic. And then we can see also about the transcriptomes, is about what genes express into a protein. So remember, DNA is blueprint, but the actual action of functions in your body is actually protein. So that's based on transcriptome. And also for the metabolomes, is actually your cell processing something from the food storage into energy. So this is the case of the metabolome. And proteomes, it will be a huge thing. It could be the structure of your cell. It could be also communications from one cell to another cell. It's controlled by proteome. And the last one is about the phenotypes and metadata. Now, in here we try to give the explanation. In our field of study, we are confronted with an abundance of information, huge information for one single patient. So remember, we not only sequence one patient. Usually we're gonna sequence 200 patients, 300 patients. And each patients, they have this kind of dimensions of data. Now, of course, we have to face the challenge of storing information. We have to try to use again DIT, like informations technology algorithms. How we're gonna store this data? How we're gonna organize this data? How we're gonna retrieve this data? And also how we're gonna normalize or transform when we compare with another database. So remember, we can took some data from hospital A, but probably the technology, if we took the sample in hospital B, is quite different. Different machines, but the same purpose. Then you have to create some algorithms in our research. How we're gonna define how we're gonna normalize so we can compare both data from different hospital, or maybe different hospital in different country, or maybe like data from different timeline, for example, from the first technology until the latest technology, which produced by the machine. Now, eventually, if we are able to solve this problem by the leveraging of foundational data from the prior data, as well as our new data, we can gain insight into the new informations and utilize it as a modeling. So we can model based on the information that we can get from the database. We try to simulate, of course, in machine learning point of view, you can train and testing our data. And also by the machine learning techniques, we can predict the future events within a group of patients. We can classify our patients. This is good patients. I mean, good diagnostic patients. This is the moderate diagnostic patients, and also the worst one, or maybe like rare variants, which is only happen like 1 every 1 million people. Now we can see like the power of the information technology algorithms to predict and also to acquire new information about certain cell. That's why machine learning is one of the most important part in bioinformatics. Now, based on this information, for example, we want to see informations of certain genetic function. We can learn, we can study new things, a lot of new things from the compound. What's the compound inside the cell? What is the gene inside certain cell in the persons? Remember, one persons have a lot of cells, so we can expect a lot of genes differences. Activate and also not activate in those cells, and also we can study what are the new functions of certain cell. For example, like COVID before COVID-19, we try to understand what are the mechanism of actions of this virus when infected to human, for example. And also we can study also cell infected by COVID, and also we can study in the more general area, like what are the disease caused by the COVID. For example, the COVID itself, when we learn about COVID, the patients died not because the virus itself, but because the virus infected the lungs. It produced a lot of like compound, like inflammatory compound, which is it causing your lungs into like a non-active or maybe like less active, and also like eventually will be leads to the organ failure. So that's the case of the COVID. So that's how they targeted the lungs. Now, because of the machine learning, it helps us not only to study a lot of things, but also we can create or maybe construct some large biological network. What are the connection between one cell to another cell? What is the connection inside the cell between these compound proteins with another proteins? And we can construct as well the network explorations, which is this is also part of our research back in the Taiwan. And also we can predict some kind of knots embedding to certain patients. Like in here, we put some color for these patients. We can put color from these patients, and we can differentiate and categorize which patients and which variant of the patients. So in here, bioinformatics apply a lot of like information technology, innovations in machine learning to process, to derive some kind of new information. So please pay attention that in bioinformatics, most of our research it try to do like pattern recognitions, because we want to recognize which one is the healthy patients, which one is not healthy patients. And as I mentioned before is like not only descriptive biology, which is we try to differentiate, but also predictive biology using machine learning. So we can predict, for example, if we have certain feature in our patients according to the genetic structure, we can predict either these patients will survive in 5 years, either they don't survive in the 10 years, and if they don't survive in the 5 years, we can also inform to our medical doctor what kind of new medications that we can bring up to the patients, so these patients can survive more than 5 years. So most of the innovations will be covered in this kind of situations in the medical health science. So in here, it will be a lot of like innovations in healthcare because all the informations have been provided into our like open database. So some of the government open their database so we can study their database, study their patients, and also compare with the another patients from another country. And also, like, for example, in my case, I can also study if I want to the patient from Indonesia and try to build some training and testing model. So back to the innovations. Now, usually in the medical science, we try to create drugs, one drugs, size fits all medicines. So this is the old style of medication. So we try to create one drug, which is this drug should be and be expected to be active to all patients, or maybe like a cure all types of patients, which is untrue because we're gonna do some stratifications because we know this is field of public health. Usually patients are grouped by the disease subtypes because we have not only one single disease. Usually disease have subtypes, subtypes 1, subtypes 2, subtypes 3, and also we have to study again about the demographic factor for each persons. For example, it's very simple. People who live in the village, rural area, or maybe nearby the forest, might be different with the people who live in the city. How come it's different? Because demographic speaking, they eat different food, they have different lifestyle, and probably they're gonna have different approach of pollution, for example. Now, based on this information, we have to separate those patients as well. And also based on the clinical feature, we have to separate the patients as well. And the last one, according to the biomarker, sometimes we have to some kind of test. We have to test our patients using the blood test, for example, and we try to predict the blood test based on the lab report to differentiate these patients is healthy one or these patients is sick one, and also these patients is the lethal one, which is it requires some kind of medical procedure is more aggressive to these patients. Now, more advanced because we have a lot of information, we have a lot of technology to differentiate between patients to patients. We can go deeper by its their genetic. For example, we know this is the same persons, have the same demographic, have the same clinical feature, have the same biomarker. But the last one, which is not the same, will be your genetic. Even the study of twin have different genetic, more specialized in the epigenetic one. So maybe the genetic will be the same, the coding with the ACTG will be the same, but the protein activate in these persons will be different. So precision medicines, we're talking about approach, which is we have to try to understand these certain patients is unique and different. So that's why it's called precise because it works only to certain group of patients, which has the similar genetic genetics information. So the innovation in healthcare, so we try to move from the traditional one, which is one size fits all medicines. We try to create one product for all people until we try to create the product or drugs to specific people or specific individual. Now, how is possible? So the next innovations, of course, we can apply new, for example, algorithms, which is a lot of algorithms in the bioinformatics research. We try to apply everything basically. So we have like in the left side, we starting from the fresh cell. We try to study the image of the cell, and based on this image, in this case, for example, we try to apply some artificial neural network to find which part in this picture is the most important part, which can categorize between this case benign and also malignant. Benign is like this is the bad one, the bad cancer. Malignant is actually low grade cancer. Still bad if we don't treat this cancer, but compared to the highest grade, benign. Maybe I switch different. Malignant is the bad one, and also benign is the good one. Now, not only we can differentiate the patients based on the artificial neural network, but also we can predict survival for all patients. So how can we predict survival? Because we have the patient data, like monitoring patients' data from day one. These patients enter hospital until the last day. It could be the patient still survive, or it could be the patient not survive. As long as we try to categorize the patients correctly, then we can predict the survivability of patients. Now, using the bioinformatics research as well as the IT research, these informations will assist medical practitioners not only tailoring more precise treatment for their patients, but also in optimizing patients' care strategies. For example, some patients have like cancer stage 4, or we can say like stadium 4 or stage 4 cancer, which is the worst case of cancer. So even the worst case of cancer, we can differentiate the persons into good or maybe bad prognostic, good prognostic, bad prognostic, or maybe like moderate prognostic. And even a stage 4 cancer, we can differentiate also the drugs that given by the patient. So it's a lot of information we can get using training and testing in our data, and also try to train our artificial neural networks to understand the patient status. So we can precise, more accurate how we're gonna treat these patients, not like just one drugs for all patients, which is that's not true anymore because we are more prone to information and technology. Now that's one of the cases in the precision medicines and also in the personalized medicines. But actually in bioinformatics, and also we are talking about the machine learning, there are a lot of like fields that we can apply to help us for the diagnostic and also prognostic. So the traditional bioinformatics, we are using genetic, and also we are using the images to predict this patient is healthy or not healthy. But also we have clinical informatics. We try to see more into population wise. So like what are the diseases more common in Indonesia? What are the disease is not common in Indonesia, but common in another country? So if you take deeper in bioinformatics research, we can get the genetic information of Indonesia. For example, 1,000 Indonesians. We can study their genetic, we can study their genes, we can study their proteins, and also we compare, for example, with the people from the four season country, for example, from Japan. We can study also the genetic one. What are the difference of the genetic? What are the disease differences in this country with Indonesia, for example? Now this will be leads to the clinical research informatics, and also part of it is the public health informatics. So we try to create some kind of data for the customer health informatics from the patients in each house, for example, and try to connect those data not only from hospital but also from your home. That's why this more like a telehealth, which is not only we try to check the patient in the hospital, we can also check our patients in the, for example, in your home, and get the information and also analyze those information using machine learning to differentiate which lifestyle is not good, which lifestyle is good for your health. Now, back to the quantum machine learning. So we have to understand these data have a lot of data, huge data. So one of the case.
Excuse me, Dr. Ezra.
Okay.
You are a bit over time. Can you finish it
Okay.
within 5 minutes?
Yeah. I can. Okay, only two slides. Okay, last two slides. Okay, one of the problem in bioinformatics, we have high dimensional data, not only your genes, but also your personality, demographic, and also clinical feature. Huge data. So this is the problem. The second data, we have to know more efficient data processing. And also we need computational power to simulating biological system. Because sometimes we try to give in drugs, but we just don't want to give these drugs to people and check the people what happened after 5 years. So we have to build some algorithms to simulate or predict what happened in the biological system if we give these drugs to our patients. Now, this will be achievable if we are using the quantum computers, because quantum computers have the potential to scale exponentially. So we are gonna produce more data in the future. So we're gonna need more computation systems to also process those data and also to store this data. So QML is the best one. So also QML, quantum machine learning algorithms, are specifically designed to leverage quantum properties such as optimizations, pattern recognitions, and also data analysis. Because the data is huge, a lot of pattern we need to solve. So maybe some kind of classical machine learning will be have difficulty if the data is way too big. So we're gonna enhance our innovations using quantum machine learning. And for the final statement, I have three final statements. So in conclusions, the fusions of bioinformatics and machine learning represents a transformative force in modern biology and healthcare. We can study more because the machine learning. And also the synergy between this discipline leads to groundbreaking advancement in understanding of biological system, how we're going to diagnose our patients, and also developing personalized treatment strategies for specific patients. And the last one, the quantum machine learning or QML, it holds significant promise for advancing biological research and also bioinformatics research, because their feature are able to do some pattern recognitions and also classifications and also simulations. Okay, so this is the last slide of my presentations. Thank you very much, and thank you for your attention.
Okay, all right. Yes, thank you, Dr. Ezra Wijaya. Okay, because of the time limit, we have to move on to the next talk. Dr. Venu Akila, have you joined the section? Dr. Venu Makila. Okay, looks like Dr. Makila hasn't joined. So let me move on to the next speaker. That will be me. So Dr. Wijaya, could you mind give a short introduction about me?
Okay.
Can you see my screen?
Yeah,
yes.
I can see your screen.
Okay, go ahead.
Okay, I will introduce my own professor. So my professor is Professor Kalok. So Dr. Kalok earned his PhD in physics at Vanderbilt University in the United States. Currently, he is distinguished professor in the Department of Bioinformatics and Medical Engineering at Asia University in Taiwan. So Dr. H has published a lot of article, which is 100 article, maybe more, professor, yeah, if I'm not mistaken, in scientific journal and also conferences. So this article cover topics such as NGS data analysis, multi-omics computational system biology, network biology, DNA data hiding, high energy physics, and polarizations of cosmic microwave background radiation. So his current research focus on using open quantum system approach to study DNA quantum biology, the use of quantum machine learning tools to identify cancer biomarkers, and also network isomorphic problems. So since December 2009, Dr. Ng has served on the editorial boards of several scientific journals. He was the editor-in-chief of the WSEAS Transactions on Biology and Biomedical. He also has experience organizing international renowned conferences, including IEEE International Conference on Bioinformatics and Biomedical Engineering, PIBE, and served as the keynote speaker at the INEGS conference on Hong Kong, if I'm not mistaken. So,
Yes.
without further ado, so I provide the microphones to Professor Kalok.
Okay. Yes. Thank you, Dr. Wijaya. Okay. Okay. This is the title of my talk: Quantum Machine Learning in Bioinformatics Research. And after that, there will be two demonstrations prepared by Mrs. Aninda Astuti and Mr. Alexson. All right. Now, because of the time limit, I may be going a little bit faster. And I also assume you have a fair knowledge about support vector machine. So this is the content of my talk. So I will briefly go over what is, okay, in this talk, I will focus on the supervised machine learning, focus on binary classification, and then talk about feature map and the kernel. And then for doing quantum computing, we have to do something we call the quantum encoding. This can be achieved by using the quantum feature map, which leads to the computation of the quantum kernel. And then after that, I will talk about the neural quantum embedding approach, which is I thought this is a rather efficient embedding approach for doing for separating the two binary classification. So after we do the data encoding, then we can do the quantum machine classifier. So we are going to do a more study about the QSVM algorithm. And then at the last moment, I will talk about the NQE, how we combine the NQE approach with the QSVM classifier in classifying metastasis data. Then after that, we will have two demo, one on QSVM and one in the QQuantum, right? Presented by Miss Aninda Astuti and Mr. Alexson. Okay, now this is a simple a diagram, a workflow diagram, which illustrates the supervised machine learning. So in which you have to extract important feature. After you extract the important feature, then you divide your data set into the training set and the test set. And then you develop algorithm to study to model your training data. So you try to build a model. Now there are many different types of algorithm. One of it is the support vector machine. The rest is like random forest or decision tree or neural net. All they have to do is to build a model based on the training data set. Now, this kind of model depends on certain hyperparameter. So you in machine learning, you try to optimize the model by tuning this hyperparameter. And the performance of this algorithm can be quantified by using something we call the statistical measure. Such as sensitivity, specificity, and accuracy, and F1 measure, and the Matthew correlation coefficient. So after you optimize your model, then you apply your model to your test data and make a prediction. Now, one of the most general, one of the most famous algorithm is the SVM. algorithm. So here we have two classes of label, the plus label and the minus label. So what you do is you want to find a decision boundary that is able to divide your data into two different regions. But yeah, well, you want to find a linearly separatable data, and but this the linear separatable boundary emits infinite many decision boundary. So you want to maximize this margin as much as possible. And the normal vector to this hyperplane is given by this normal vector W. Now this is the vector equation for this free hyperplane. If you set equal m equal to 1, then you get this. So so you want to make to adjust your the W vector so to maximize this margin. So by maximizing the margin, so the margin is given by the m over the magnitude of the W. So in order to maximize the margin, that means you want to minimize this W. So that means maximize the margin imply you want to minimize the W, but it is subject to the M constraints. There is for the positive label and the minus label, it has to satisfy an equation like this. Y is the class label, which could be plus or minus. W is the parameter, okay, the weighting parameter, and T is this is just the bias parameter. So in two dimension, if you consider two features, so that you have x1 the I label xi data times the first feature, and this is the second feature. So here we do not allow any misclassification. So there is no in this case, there is no data point sitting in this margin. So there's no misclassification. This is an ideal situation, but in real situation, you do have data point sitting within this boundary. So we will take care of this later. So this kind of a problem is the so-called quadratic constraint optimization. So so you have to minimize this function. It is more convenient if you use a W square instead of W. And then you have to include this constraint by introducing the Lagrangian multiplier with the label index alpha I. So so this is the so-called the cost function, or the so-called the Lagrangian. Now this form is not easy to do. So what people usually do in the support vector machine is to transform this form into the so-called dual form. And the dual form has a nice property that is you can look for the similarity of your data point by computing the dot product of your input data. So this problem has a time complexity for solving the dual form. If we start with M data, each data has n big N features. Then this is proportional to M squared. and finding the alpha coefficient is the order m cube. And doing the dot product is a order n, depending on how many features you consider. So in total, you have the m cube plus m squared times n, and then scaled by this logarithm 1 over e factor. E is how fast is you can converge to your solution. So this is a polynomial time complexity. If we can, it turns out for certain quantum algorithm, you can achieve much faster with the logarithm time complexity. So we're able to achieve exponential computation power. Okay, so what we do in quantum machine learning is before we input our data in, split the data into the training set and the test set, we map the classical data to a quantum state. This is the so-called the quantum encoding stage. So in the next few slides, I'm going to present something about this encoding technology. We have seen a lot of biomedical application for the use of quantum machine learning and classical machine learning in the past couple of years. Like this is about the study of non-small cell lung cancer patient, and also in studying biochemical systems. Now, if we can map the data into the quantum state, that is the state is living in the Hilbert space. Now, what is the advantage of doing this? The advantage is by doing this, it allows for better expressibility. So that means you can have a model that can explore a larger portion of this Hilbert space, and you can represent more function. Another advantage is for the quantum state, we can perform well on inferring pattern and making a more accurate prediction on new data. And another advantage of the quantum model is it is easy and efficient to be trained. That means it can optimize very effective. It is easy to adjust the parameter of a quantum circuit and minimize the cost function. So a higher trainability means the model can efficiently train. That means that you can find the local minimum very efficient. But there is some trade-off. High expressibility may lead to lower trainability. This is the so-called balloon plateau problem. I don't have time to talk about this, but I refer you to this paper. So, so this kind of a feature advantage is sometimes is not compatible. So people are trying very hard to bypass this balloon plateau problem. In other terms, you use in the quantum machine learning is the so-called effective dimension. That means a higher effective dimension means the model can express more complex function. It can be generalized better to new data or unseen data. So given input data, say n samples, with each one has f features. For instance, like the iris flower, we have 150 sample, and each one has 4 features. right? And you want to design a mapping function. So to map your number to the quantum state. So there are many mapping function. One of it is a exponential function, in which it depends on your input data. So here we have the encoding function, say encoding function phi1, phi2, phi3. And we have the Pauli matrix sigma z and I, or sigma z dot sigma z. So if we have we transform the data into 2 qubits, and this is the form, okay, acting on a 2 quantum bit. So maybe yeah, it's here I have 5 qubits, and then we have the Hadama layer acting on this 5 qubits. This symbol means tensor product, and then we have the U phi function, and you have many different choice of the U phi. In this, this is only one choice. So what you do is you try to map your data into a higher dimension. So with a 2 qubit, we have a 2 to the power 2 qubit space dimension. Now you have many different choice of phi1 and this tensor product of the Pauli matrix. So here is just one form. Say phi1 is equal to x1, phi2 is x2. So this x1, x2 is referring to the 2 features. So, and then you transform your data from 2 dimension to a 3 dimension, because we have a 3 functional form over here. So you have many different choice of this phi. So this is the way how we to express this this quantum transformation. That is from for the figure we move from left to right, but for the matrix operation, so we hit this Hadama first 5 times, and then we have the U phi next, and then we hit the Hadama tensor product 5 times, and then we hit the U phi again. And so we have you can use a multiple layer. Okay, the more layer you use, suppose you can have a higher nonlinear degree. So this is the way we do. We transform our data into higher dimension and hope that the data can be linearly separatable. Now there are some mathematical technique that you need to learn because we are considering the exponential of a matrix. So what you do is you expand the matrix in the Taylor series form. Now, depending on this matrix Q, right? Because here we have this sigma c times identity, and I sigma c and sigma c times sigma c. You have this kind of matrix in the exponential. Okay. Now, this matrix may be diagonal, or it has a non-diagonal form. So if we have the diagonal form, suppose the matrix is like this, then it is easy to take the exponential of this matrix. It's just you insert the exponential of Q1, exponential of Q2, and so on. Now, if Q is not diagonal, But you can diagonalize a matrix with by solving the eigenvalue equation, and then and look for the diagonal form for the Q matrix. And the diagonal matrix and the Q is related by this P matrix. The P matrix is built from the eigenvector. So for non-diagonal Q, if you want to find the exponential of this non-diagonal Q, it is equal to the P times E diagonal and P inverse. So this can be done. Now, you have another two situation is sometimes you want to multiply two exponential of a matrix. Now, in a real number, the EQ plus R is equal to EQ times ER for the two matrices commute. But in general, the matrix may not be commute. So in that case, you cannot, it's not that simple. You cannot write the EQ times ER is not equal to EQ plus R. It is given by this matrix S, which is Q plus R with some other terms, some other additional terms. This is the so-called Baker-Campbell-Hausdorff formula. So if like the control C gate, it is diagonal. So you see with the then the exponential of this is easy. And for the rotation gate, this is the rotation C gate. This is the matrix for rotation gate. And then the exponential, this is the exponential of this the C gate is diagonal. So it is easy. Now, just now I show you a simple form of the feature map. We have the embedded function, and then multiply this by the Pauli matrix. So this is the general form of the mapping function with the summation, right? Vs times the Pauli matrix tensor form. So this form is yeah, just do not feel this is complicated. It just means that we have a summation, right? We just write this plus plus with a summation. And then we have the embedded function times the tensor product of the Pauli matrix. So this is only one of the special form of this expression over here. Yeah, although it may look complicated, but if you consider the particular case, it just means the embedded function times the tensor product of the Pauli matrix. Now, this right now I only consider the k equal to 2. That means I take the tensor product of two matrix. So from 4 matrix, I can form 16 possibility. So sigma C I is one of it, sigma CC, or sigma XY, sigma X, sigma Y. You can form more terms, okay? That means we are not restricted to only mapping the data to 3 dimension. You can map this to a hyperspace with 16 dimension. Okay, so this is the circuit that we use. We draw this from the IBM QSKIT. So like what we have the Hadama, and then we have the unitary phase gate repeated 2 times. And down here we have the Hadama, and then the unitary gate, but now with the entanglement. So we also have this two repetition. So this one is this is the so-called entanglement gate. We entangle Q0 and Q1. Of course, you are not limited to use the very simple encoding function here. You can include more complicated nonlinear function. So like here, this is an example of a 3-qubit Hadama, and then the phase gate, and then the control NOT gate for Q0 and Q1 qubit, and then for the entanglement between Q0 and Q2, and then for the entanglement between Q2 and Q3. So this is one of the CC feature map. You can repeat this many times, but the more you repeat, then it has more, is subject to the quantum noise. So by doing that, then once you build the feature map, and then you combine your quantum circuit, then you can create the so-called quantum SVM classifier. And the kernel function is the dot product between this embedded quantum state. Okay, now the people try very hard to develop a quantum embedding technology. Okay, people use different names, say quantum feature map or quantum encoding or quantum embedding. It's just the same thing. So what they try to do is they try to separate your data in a higher dimension first. So before they input that into the training data, they make use of the quantum feature map technology to separate your data first. So they try to maximize the data separability of the two classes. So this is the technology introduced by these people in this paper, quantum embedding for machine learning. So here they propose the quantum metric learning method to maximize data separability. And the data separability is quantified by a distance. Just like in machine learning, we introduced the Euclidean metric to quantify the separability of two data points. So, but in quantum, they use something called a trace distance or Hilbert-Smith distance. The advantage is it can achieve a good embedding using a small quantum circuit. Now, another one is the so-called NQE. This is because when they do the quantum embedding, they still use a quantum circuit, which is still subject to noise and need more repetition. So NQE, they use a classical neural network to train the input data. Now, just now, I only specify the mapping function, right? The mapping function is the encoding function that is, say, for instance, say the phi1, phi2, like this form, okay? Now, but we do not know which mapping function is optimal. So in the NQE approach, so what they are doing is they use the neural net to train the mapping function. So you can have a higher level of data separability. into two orthogonal space. That means the plus label and the minus label. So this is the contribution from this publication over here, right? So what they do is they have the input data, and then they have the layer, and then they train the mapping function. So once they train the mapping function, then they build the unitary gates. And then they do some measurement, and then compute something called the fidelity. This is done by the quantum computer. So they can optimize this mapping function instead of the very simple one, phi1 equal to x1, phi2 equal to x2. So the contribution of this method is they allows you to work out to train and find the optimal embedding function. So this is the contribution of this embedding technology. And once you do the data embedding, then in our bioinformatics metastasis research, where we use the quantum SVM for classifying the data. So that means here we use quantum embedding technology, the neural quantum embedding, and then we use a QSVM in here. So we are talking about the technology over here. Now, in order to achieve to make advantage of the quantum computing, we have to use the so-called least square support vector machine. This is because the least square support vector machine allows you to solve the problem more efficient than the other variant of SVM formulation. So simply saying is you have to consider the Lagrangian, but now what do they mean by least square is if we have some mislabeled data points sitting within sitting within the margin of the hyperplane, you have to do some adjustment. So this is the so-called soft margin optimization. So for the least square, that means that this term is quadratic instead of a linear. Now it turns out this form is they can have a more efficient quantum calculation. So what you do is with this Lagrangian, like in the classical machine learning, you take the partial derivative of this Lagrangian, and then you get a system of a linear equation. So this is the system of the linear equation with the kernel matrix, and then the B is the so-called bias parameter. Alpha is the Lagrangian multiplier coefficient. So what you have to do is, this is in the classical form, right? So what you do is you have to translate this into a quantum state. So if you can, the people find the way to do it, okay? So they transform this linear system equation into a quantum state. And this quantum state will describe the hyperplane. So once you have the hyperplane, then with a new data set, with a new data, you can transform the data into the quantum state. And then you can classify your new data based on your B alpha quantum state. You can be classified it as either -1 or +1. So this is the general idea of the least square support vector machine. Now, this is for more detail, please refer to this publication. So in our bioinformatics metastasis classification study, this is our workflow diagram. So what we did is we do data dimension reduction, and then after that we do the NQE data embedding. After that, we classify our data using a classical support vector machine as well as quantum support vector machine. And then we compare the performance of these two approach. I will skip this. This is our input data set from the kidney the metastasis sample. One sample is non-metastasis, the other one is metastasis state. And this is when we using the neural net. Remember, we use the neural net for training the embedding function, and it turns out the training loss decrease as we have more and more steps. This is the situation for 9 principal component, 10 principal component, 11 and 12, and we see the training get decrease as we have more iteration. And then after the use of the PCA NQE data embedding part, then we do the support vector classification as well as the quantum support vector machine classification. So here we see the left one is the use of the classical classifier, and the right one is the quantum support vector classifier. So here we use many performance metrics, and you see for 9 component and 10 component, the 9 and 10, the 9 is the green one, the 10 is the red color one. It can achieve a bit better true positive rate, and it can also achieve a better false positive rate, false discovery rate, and false negative rate. The lower is the better. Say here we have something lower for 9 principal component, as well as for 10 principal component. But the classical support vector machine still has better classification performance for 11 principal component and 12 principal component, because they have a lower false negative rate compared. So my conclusion is we have present a method of quantum embedding and NQE. Our findings suggested that using PCA NQE to preprocess the data set could improve the QSVM classification, surpassing a traditional SVM in certain conditions, but not in all situations. All right, so for that, I'd like to stop and then move on to the next speaker for the demonstration. So let me see, this is my introduction, yes. Okay. So I'd like to introduce our next two speaker, Aninda She's currently a PhD student in Asia University. She obtained a bachelor degree in informatics system from Amikom University, Yogyakarta, Indonesia. And she obtained a master's degree in computer science and information engineering at Asia University, Taiwan. Her areas of interest include artificial intelligence, machine learning, deep learning, big data analysis, computational fusion algorithm, and quantum machine learning. She and her team member won the Special Enterprise Award at the NTU IBM Quantum System 2023 User Conference and QSKIT Quantum Computing Hackathon, Taiwan, 2023. And then our next speaker is second speaker is Yun Chen's son, Alex. He's a doctorate candidate in the College of Computer Science and Information Engineering of Asia University. Yun Chen used to serve as the Vice General Manager and Chief Information Officer of Taiwan Land Development Company and the Software Director of Honghai Foxconn Group. He focused on software architecture development and design, team leadership, project management. Current research area include AI and robot application, as well as quantum large-scale computing. So for that, I'd like to pass my microphone to Aninda. So Aninda, can you share your screen?
Yes, Prof.
Okay, now because of time limit, so I suggest Aninda and Alex, could you finish your presentation somewhere between 10 minutes and 15
Yes.
minutes?
Yeah.
Yeah, okay. All right. Okay, I can see your demo. Okay.
Hello, everyone. I'm Aninda Astuti. Today, I would like to doing demo in quantum support vector machine. So, agenda for today demo: one, quantum kernel; second, breast cancer classification; and the third, managed digit classification. In quantum kernel, now we use QSKIT machine learning 0.72 to do QSVM classification. In here, we will use the fidelity quantum kernel and then QSVC class. In here, I provide the resource or tutorial about the new mapping of the machine learning, QSKIT machine learning. For the machine learning, QSKIT machine learning, we have to look up the diagram or the architecture of the QSKIT itself, because they often to do the upgrading the version. So now I continue to present about the breast cancer classification. So first we have to import the package. This is standard library from the QSKIT. For example, for visualization and then widget quantum circuit. Also we have sampler and estimator. And then we import the standard package for Python code. And then we load the breast cancer dataset from Sklearn dataset. This is the data feature, and then this is the class label, and then this is the column name. We rename the column based on the column name in the dataset. So this is how the breast cancer datasets look like. In here we have 100 samples and then 30 feature. with two class label, 0 and 1, 0 for begin and 1 for malignant. So 50 for class 0 class and then 50 for 1 class. After that, we do the dimension reduction. Why we have to do that? Because when we run the QSVC, we have to we cannot do a larger circuit because this is will be take the time consuming. In here, we reduce the dimension using 4 components. And then after that, we split the data for training 80% and then for test 20%. So do the machine learning, Qiskit machine learning, we have to install the Qiskit machine learning package in here. And then after that, we use the fidelity quantum kernel class. We use the sampler. This is used to calculate the quasi-probabilities of the bit string from quantum circuit. And then we put the sampler to the fidelity function. This is represent of this equation. So if we set the sampler to the 0, then means the default of the parameter will use the compute uncompute. And then we do the feature mapping by using the ZZ feature map. In here we use 4 qubit and repeat it 1 times. For default, they use the 2 qubit and repeat 2 times. In the ZZ feature map, this is represent of this equation. And then we plot the ZZ feature map. This is how our ZZ feature maps look like. We have the 4 qubit 0, 1, 2, and 3. And then we have the Hadamard gate. This is represent of the Z feature map. And then this means the 2 qubit entangled together. This represent the ZZ feature map. And then this is based on the classical nonlinear function. Q0 and Q1 until X0, X1, Xn, this is represent of our feature, our input feature. After that, we do the classification by using QSVC. This is how we call the kernel, and then we plug the kernel to QSVC function. And then we feed our training data set, and then we test by using our test data set. And we get the result for accuracy in here 0.4. And then we also try to use the 2 repetition. We got the accuracy 0.65. For QSVM, they have the 2 approach. One, we directly can use the QSVC and then call the kernel function, or we use the classical SVC and then plus quantum kernel. By using the SVC plus quantum kernel, we have to put the function evaluate in this part, and then for fit the training and test the dataset is the same, and we get the same result for accuracy 0.4. In QSVM, they also allow us to do hyperparameter tuning, so we can find the optimal C and gamma by setting the parameter on data map function in ZZ feature map. In this part, we can do this one by using the grid search, and then we can use RBF kernel to do hyperparameter tuning. Now I move to manage disease classification. This is for the image classification. Same as previous, we have to import our library, standard library for Qiskit and standard library for Python or for using pandas. In here, we load the data set by from the keras. In here, we use the 100 for training set and then 50 for test set. Before we pass to our data to QSVM, we have to normalize the data. And then we reshape our training image into a true 2D array. This is how we reshape our image. And then how this is the representation of our data set with the class label in here. So our data set contains of 150 samples, 100 for training set, 50 for test set. And then the feature content of 784. This is from the 20x times 20x the image. Two class label for class 0 and 1. And then we can plot our data set. This is representation of our data set 0, 1, 1, 1, 0. It's the same, we have to do the dimension reduction. In here I use 4 pieces for the dimension reduction. This is how our data looks like after dimension reduction. And then same as before, we have to create the fidelity quantum kernel before we pass our data. And then we plot the ZC feature map. This is, we use the 2 repetition. And then we classified our data using QSVC. The output of accuracy score is 0.57. And then by using SVC plus quantum kernel, we get the same result. And this is the reference when we want to study about how we do classification by using QSVM.
Okay, all right. Thank you, Mrs. Aninda. Very nice demonstration. Okay, and let's move on to Alex.
Yes, Professor,
Okay.
can you hear me?
Yes, I can hear you. So can you share your desktop?
Okay. Just allow me to share the screen.
Yes. Okay, good. I can see it.
Okay,
Yeah.
you can see again. Okay.
Okay, so because of the time limit, please finish it somewhere between 10 to 15 minutes.
Okay. I try my
Yes.
best.
Okay.
Okay.
Yes.
Hello, everyone. I will to introduce the NVIDIA Cloud Quantum reflection and the source. Okay, today. And first, this is our agenda today. And I will focus on the CUDA quantum and to present some installation. Okay. And I will to compare some different software tools, such as QSVM and the Google Quantum AI, and also the NVIDIA cuQuantum. Okay. Okay, and but in today's demo, I will to demo the cuQuantum installation by Docker first, because I guess we don't have the time to demo the QNN with means the data set, because also I honestly got a little trouble with the QNN. Okay, first who I am, who am I? Okay, I have worked for the software industry for many years. This picture is which company I was worked for a long time ago. And right now I'm focused on AI and the robot application, robot application. And also we want to make an small AGI, artificial general intelligence. And we want to achieve about the quantum large scale computing. Okay, so first of all, we talk about some conceptual or the conceptual idea. What is the cuQuantum? According to NVIDIA's advertisement, that is the platform for hybrid quantum classical computing. Yes, so they provided an bridge technology. This kind of bridge is between the quantum computing and the classical computing. Also, the classical computing is meaning for the HPC, high performance computing, or high performance computer, or some kind of supercomputer. At least use the NVIDIA A100 or H100. And in some software architecture idea, we were to develop first some conceptual, then we can draw a conceptual diagram. According to this conceptual diagram, then we can develop some architectural diagram. Yeah, and that is the software system architecture. Yeah, to explain the what we saw and what we discover in the used to the in the software system. So that is we discuss the cuQuantum architecture diagram on next page. So let me give you some brief history of the cuQuantum. Okay, first is the QODA, quota, the quantum atomized device architecture. Okay, it's announced on the 2021. And second, become cuQuantum. This is some accelerated quantum computer research SDK. So the cuQuantum is mean a large and a package of the algorithm, yeah, for the accelerator. Okay, and that is announced on the 2022. And finally, last year, 2023, November, the NVIDIA announced the cuQuantum. Yeah, so cuQuantum is the combination these two conceptual. Then it become a bigger, very large platform. Yeah, for the quantum computing. Yeah. Okay. And we also need to study the CUDA, Computer Unified Device Architecture. This is developed almost over 20 years. Yeah, CUDA is a very, very mature technology, and that is the NVIDIA itself to, and that is a very, very important developer technology by NVIDIA. Okay. And it also become an ecosystem. Okay. The next presentation pages show about the cuQuantum architecture. Okay. Just in the right of the picture. Okay. And the top of the picture is to talk about the hyper application. That is our application layer. Yeah, application layer. So that is mean all about the software application. Yeah, so we can apply in many different variant domains. Yeah, for example, some chemistry, weather, forecaster, logistic, and more and more. Okay. Then the kernel is cuQuantum. Okay, cuQuantum, the platform, and the next level is you see the system level tool chain, because the cuQuantum use many different tool and the technologies, especially the NVQ++. What is this? NVQ++ is a compiler. Yeah, and this compiler is useful to compile your source code, your high-level language source code. For example, Python or C++. Yeah, the software engineer can write some Python program or C++ program. Then by the NVQ++ to translator and compile it to some kind of binary code. Okay, to send it to the GPU. Okay, NVIDIA GPUs there, and the other content resource. Yeah, so the last level is the hardware level and hardware device. Okay, so keeping in mind, we know CPU. I think everyone knows what is CPU. Yeah, and everyone know what is GPU. Yeah, but right now we need to study an QPU, quantum process unit. Okay, this is the hardware device. Okay, then we can use the QPN to present qubit and also the quantum circuit. Okay. Do you have any question? Okay, let me continue. Okay. And NVIDIA has to guarantee the scalability, yeah, and the performance by crossing the quantum. Yeah, you can separate it into many GPUs kernel. Okay, let me just talk about the architecture conceptual more. Here in the left side is the software stack. Software stacker is the software, many software stacker together. Okay, and the final, the lowest layer is the hardware there, and there is the firmware, and the hyper operation, and the OS driver, and the routine, and also and so on. Yeah. So this is a traditional way, or is a cooperation way, or we can say that is an orchestra way to combine and unify the architecture. Yeah, for the applications. Okay. And how it works, how the cuQuantum works. Okay, and we need to introduce more conceptual here. Okay, for example, in the system diagram, in architectural diagram, you will draw input or output. Yeah, you put an input and we want to get the excitation output, right? And that is, we can use the API and or SDK. Yeah, we software system providing API, yeah, and also SDK where we can manipulate these two packages then to get the result. And then you also use an MQ or NPI. IBM have a tool, it's called MQ or message queue. And also NVIDIA providing an MPI. MPI is a message passing interface. Yeah, and then you can pass large of scale numbers. Yeah, also especially for the tensor. Yeah, TensorFlow. Yeah. Okay, so this is a communication way in the MPI, communication protocol. Okay, so there are three different pictures. That means in generally, we will put 320 gigabytes state vector into different GPU. Yeah, GPU 1 to GPU 4 is a general solution. If you write some OpenML, OpenMP, okay, that is a traditional way to serve the parallel computing. Okay, and if you use this kind of MPI or cuQuantum, then you can separate it into a different GPU by automatically, yeah, adjust the quantum cuQuantum platform. Yeah, it will to automatically to balance the calculation. Yeah, and also if we define the last picture on the bottom, we define the GPU 1 and GPU 2 is some kind node, and another GPU 3 and the GPU 4 is another super node for the quantum computing. Yeah, so the cuQuantum, NVIDIA announced they just need to 160 gigabyte state vector to be the training data and to use to the different two super nodes. Yeah, that is much convenient and reduce the calculation mountain. Yeah. Okay. Here become the compare time. Okay, I will compare a little bit about first the IBM QSKit. Yeah, IBM QSKit. Let's present Aninda is very familiar with the QSKit. And QSKit, when I work with the QSKit, I found it is the most popular quantum software in the world. Okay, so we can use this link to get our Python virtual environment. Then we can install the QSIC runtime environment. Yeah, that is very convenient. Also, it can use on the Windows platform. So I didn't make a this presentation. Okay. Next is we can compare with the Google Quantum AI. It look like some quantum frontier. Okay, and I would say that is very most convenient teaching courses in quantum computing. Okay, and also their teaching their courses is always announced on the Colab. Yeah, so that is very convenient for the beginner to learning. Okay, so let me to share some information, web page information here. Okay, so you can read this page. Okay, okay. So what is the Google want us know the feeling about the quantum computing? You see, explore quantum AI. That is the traditional way. If we want to explore something, for example, this web page or this picture, then we can have a very special focus, and we can look around everywhere. Okay, and another way to think about this is this kind. You see the foxconn? Oh no, you see the fox? Yeah. Okay, we can move our mouse cursor everywhere, and he will tracking. Yeah. That is some kind of GPU kernel thinking. And what is the Google want to tell us? Sorry, I cannot move the video.
Hey, sorry, Alex. We have 5 more minutes. Can finish.
Okay.
Yes.
Okay. Here's another way. It's a quantum thinking. Yeah, everywhere, every quantum can help you to do the calculation. Okay. Okay. And finally, it's the NVIDIA Quantum. They may be the most powerful HQC, yeah, for the hyper quantum classical computing. Okay, then we try a little bit about the installation demo. Okay.这台是167吗？应该是。反正那台是167嘛。对。那用什么账号进去？对啊，26。 Okay. The cuQuantum only can use on the Linux-like system. Okay, so first we need to check how many images you download. Okay. Okay. You see, I already download 5.94 gigabyte. This is the cuQuantum image from the NVIDIA, and then you can also use the Docker to download it. And I also provided the instruction on my PowerPoint. So don't worry about the instruction. Okay, right now we are running the Docker because we are activated the Docker environment. So you see the pump size changed. Right now we are in the cuDA-Q. It's the short name of the cuQuantum in the early days. And also we can make an examination, or we try to use Okay. Let us try to execute the two programs. First is the cuQuantum backend. That means you can, according this.
You need to change the directory to some other directory, the Python, right? Change the Python system, but I don't see Python. Yeah, up down below examples. Yeah,
Oh,
change.
Too many directories.
Okay, so sorry, Alex, can you finish it within 1 minute? Because we are over time. Okay.
Okay. Maybe we just try another. Okay, this is our first example with 1, 2, 3, 5, 4, 6 quantum bits to make a quantum circuit. Okay, thank you.
Okay, all right. Okay, thank you, Alex and Aninda for the nice demonstration. Now, since because we have already a bit over time, so I think we only have time for one question. Are there any questions from the audience? Okay, looks like we don't have any question from the audience. So for that, then I would like to conclude my our presentation for today. And then next week we also going to.
Have. I'm sorry, Professor. I think they have the question in the chat box.
Yeah, but I don't see any message in the chat.
Oh.
Yeah, I don't see any. Right.
They have some messages for the.
Here's my chat, but I don't see anything. Can you see my screen?
Yes.
Yeah, I don't see any question in the chat box.
Oh.
Or you can see that?
Yes, I can, Prof.
So can you post
can
or message? Yeah, post it in the chat box.
Yeah. Okay.
I don't see anything in my chat box.
I sent already by line, Professor.
Okay, all right. So let me see by line. Okay, the first question is there a certain threshold value that describe? Oh, no, those are the question for last week.
Oh.
Yeah, it's not for this week. Yeah, those are the questions for last week. Dr. Hillman and Wiki's talk.
Yes, Prof.
Yes. Okay. Okay. Then if not, then I'd like to remind you next week we are going to have Dr. Hillman and another a fellow from the institute to give a presentation on the quantum, I think on the autoencoder. Okay. It will be the same time, I suppose, but I will keep you informed and post. All right. So thanks again for joining us at this